Okay, I'm going to do the first problem from last semester's exam. It says, circle the correct answer, write some sentences, or show a calculation explaining how you obtain the answer. Okay, so we have a uniform electric field of magnitude 1,000 newtons per coulomb pointing in the negative x direction. So our field is this, 1,000 newtons per coulomb and in the negative x direction. Calculate the electric potential difference VB minus VA between the points A and B. So between this point and this point. So the potential difference is the work done to move between these 2 points. So VB minus VA is V final minus V initial. So that means that we're moving from point A to point B. So we have to choose the path that we're going to move. So we'll go down, just perpendicular to the field, and then we'll move parallel to the field over to point B. So let's think first, this part of the path won't contribute to the work at all, since in order to move the particle from here to here, we need to apply a force in the positive x direction. So the electric field would push it in the negative x direction, and we're going to have to counter that force in order to move from here to here without any velocity. So we're applying a force per charge in this direction of 1,000 newtons per coulomb, and that's in the positive x direction. That's our force. So from here to here, our displacement vector is in the y direction. Our force vectors in the x direction, so those are perpendicular, and force dot displacement vector will be 0 for this part. So the work done to move from here to here is going to be 0. Then now we need to move from here to here. And so we're going to apply our force still in the positive x direction to cancel the force due to the electric field, but now our displacement vector is from here to here is a positive 4 centimeters. So our force vector is 1,000 newtons per coulomb in the x direction, and the displacement vector is 0.04 meters in the x direction. So the potential difference from A to B is the work done, which is the force times the distance, since it's just a constant force. So 1,000 newtons per coulomb times 0.04 meters is 40 newton meters per coulomb, which is 40, a newton meter is a joule, so this is 40 joules per coulomb, or 40 volts. So this is the correct answer. And we knew it was a positive answer, so we could have just eliminated these initially, since we're going to apply a force with the field. So we're applying a force in the direction we're going. So we're pushing in this direction and we're moving in this direction. So that's a positive force. We could have also chosen to move in a different direction, like say to move from A to B directly instead of down this path and then this way. So we could have done this. If we had done that, then we would get the same answer, but we would have chosen the force we're applying is the same, so 1,000 newtons per coulomb, and that's still in the positive x direction. So no matter what path you take, we're just applying a force to cancel the field. So the force would have been the same, and the displacement vector, if we had done this, would have been minus 4 centimeters. So positive 4 centimeters in the x direction and negative 4 centimeters in the y direction. And then by taking the dot product of this and this y part doesn't matter, and we'll still get the same answer. So this different path you could have chosen to get the same answer. Okay, so let's do part 2 here. It says the electric potential at the center of a circular ring of uniform charge density of radius r is V at 0 is 2 pi k lambda, where lambda is the linear charge density. And so the figure here shows a different circular ring with 2 different charge densities on equal halves, so lambda 1 and lambda 2. And they give the radius of the circular ring is 1 centimeter, and we want to find the electric potential at the center. Okay, so we know we have some charge that's evenly distributed over this part of the ring. And that charge density is in coulombs per meter. And we have some other charge density over here. So we have a negative charge over here, positive charge spread out uniformly over this part. Okay, so we can kind of just ignore this actually. We've got to think about it like adding up all of the potential due to these individual charges that are spread out over this ring. So we want to add up on this half of the ring, what is the effect of each individual charge on the potential at that point? And then we'll add up over this part of the ring the effect of all these charges on the potential at that point. So the potential due to a single point charge, some distance, this is at some distance r, is the radius of that circle. So the effect on the potential here from a point charge a distance r away is V is k q over r. So that's for a single point charge q, a distance r away. But now we want to add up what that is over this whole part of the ring. So what we would do is do an integral over all of the charges, k dq over r, basically, but they're all at the same r. So this would actually just be k over some constant r times integral over all the charge. But an integral over all of this charge is just however much charge there is. This is just the total charge at that point. And we know the charge density, and we know that the length of this is just half the circumference of a circle. So 2 pi r over 2, just get pi r. And so from this half, adding up all of the contributions of all of these charges gives us a potential at the center of k over r times the total charge, which is just this charge density, lambda 1, times the this part of the circumference. So just pi times r. And that's just this side. So now we add up this side. The k and the r come out in the same way, and we have lambda 2 times pi r. So these r's cancel this one down here. We get v is k, pi pulls out, and lambda 1 plus lambda 2. So if you plug in the numbers for this, k was on the very front sheet, so k is this here, 9 times 10 to the 9 newtons meters squared per coulomb squared. So the potential is k, 9 times 10 to the 9 newton meters squared per coulomb squared, times pi times lambda 1 plus lambda 2, which is negative 10 nanocoulombs per meter. And so if you solve this, you'll get negative 283 volts. Okay, let's do problem 3. We have several 1,000 watt hair dryers plugged into an outlet strip powered by 120 volts. The circuit breaker will shut off the circuit when the current exceeds 20 amps. So we want to know how many hair dryers we can turn on without tripping the circuit breaker. Okay, so we have 20 amps total. Each hair dryer will require some amount of current, and we need to figure out how much current each hair dryer uses and make sure that we have fewer than less than 20 amps total from the hair dryer. So each hair dryer has a power of 1,000 watts, and that is the current times the voltage for each hair dryer. So the current per dryer is this power, 1,000 watts, divided by the voltage that it's used at, which is 120 volts. So this is 8.33 amps. This is per hair dryer. So the maximum we could use is just 2, because otherwise we would go over our limit of 20 amps and our circuit breaker would break. So the answer to this one is 2. For part 4, 4 here, we want to find the current leaving the battery in this circuit. So what we need to do is take this circuit and turn it into a simpler circuit where we can just apply Ohm's law and find the current through the circuit. So we want to turn all of this stuff, these resistances, into an effective resistance. And then we can just say that our circuit is a battery and some resistance are effective, and then the current through it will be just given by Ohm's law, where this is R effective and this is the voltage of the battery, 10 volts. So we need to find some R effective that will be the effective resistance of this whole circuit. So the way to find effective resistances is to break down a more complicated circuit into smaller effective resistances. So the first part, we need to find any parallel or series resistances, and then we can break that down into an effective. So the first part of this one is that these two resistances here are in parallel. So we have two 100 ohm resistors in parallel. So that gives us an effective resistance here of these two resistors of 50 ohms. If you have two parallel resistances and those resistances are equal, then the effective resistance is just half of each one. But you could just solve for that if we had different numbers or something. So if this were resistor A and this were resistor B, then 1 over the effective resistance is 1 over RA, so 100 ohms, plus 1 over RB, it's another 100 ohms. So that's 2 over 100 ohms, and we'd get R effective for A and B is 50 ohms. So now that we've got an effective resistance for these two resistors, we can say that we can redraw our circuit as we have a battery, we have still here this 50 ohm resistor, and here this 100 ohm resistor, but now in between we have our effective resistance of 50 ohms from these two resistors, and this connects like that. So now we need to break this down more. We have these two resistances, this one and this one, are in series, so they just add. So if we redrew a new circuit, we would have our battery, and now these two become 100 ohms. And then we have this 100 ohms still in parallel with that. We can break these two down into an effective resistance again. We have 100 ohms and 100 ohms in parallel, and we already found that that was 50 ohms. So that means that we have our battery, 50 ohm resistor, and that's it. That's our effective resistance of all of this stuff. So this was voltage of 10 volts, and it's using Ohm's law. We have 10 volts is the current times the resistance of 50 ohms, and so we get a current of 10 over 50 amps. So a fifth of an amp is this right here, 0.2 amps.